Welcome back to AI.Code.Cast. So, uh, you know how sometimes, like in coding, you have to find the longest unique sequence within a larger string?
Oh, yeah.
Like, imagine you're sifting through, like, DNA strands, right? Like a scientist, and you're looking for a gene sequence, like one that's got the key to something really groundbreaking.
Yeah.
That's kind of what we're doing today. We're tackling the longest substring without repeating characters problem. It's a classic.
It is.
And it's everywhere. Like, seriously, coding interviews to real-world applications. Like, any place efficiency matters.
What's so interesting is it sounds super simple at first glance. Like you've got this string, and you just need to find the longest part of that string with no repeats, no repeating characters. Sounds easy, right?
Right.
But how you actually go about it, it can make all the difference. Like between a solution that takes forever and one that's, well, blazing fast.
Okay, so let's break it down a little. Let's say we have a string, just like abcaps even. What would be the longest substring? The one without repeating characters in that case.
In that one, it would be A, B, a C,
Okay.
which would give us a length of 3.
Okay.
It's important to remember we're talking substrings here. So those characters, they got to be next to each other.
Right.
Consecutive.
Gotcha. Like if we had like PWQ, we couldn't just pick out like book.
Exactly.
Because they're not like right next to each other.
Nope.
So it'd be book with a length of 3. And that makes me think though, if we had a really, really long string, wouldn't it take like forever to check every single substring?
You're totally right. Yeah. I guess you could call it the naive approach, the brute force method. You'd be checking every single substring to see if it had unique characters. And while it's easy to understand.
Right.
It gets wildly inefficient the longer that string gets. Like imagine trying to find like the longest unique gene sequence, but in a DNA strand with like millions of characters.
Yeah. Yeah, so how bad does it actually get with this brute force approach?
Lay it on me.
Well, think about it this way.
Yeah.
To get all the possible substrings, you'd basically be using nested loops.
Okay.
Right. So that right there, that gives us O of n squared time complexity.
Okay.
Then, for every single substring, you got to check, does it have duplicates?
Yeah.
And worst case, that could be another O of n time.
Oh, so we're talking O of n cubed time complexity. Oof, that's painful. Like watching paint dry 3 times over.
Yeah.
We need a better way, a smarter way. Can we even avoid checking every single substring?
We can. And this is where the sliding window technique, it kind of comes to the rescue. It's way more elegant.
Okay.
So picture this. It's like a window moving across our string. It expands when it hits new characters.
Right.
And it shrinks if it encounters a duplicate.
Okay. I'm kind of getting the visual.
Yeah. But how does that actually help us find the longest substring?
The key here, we're just focusing on a piece of that string at once.
Okay.
Right? It's that window.
Yeah.
We're being strategic. We're adjusting it based on what we find. And this lets us process the whole string in linear time.
Right.
Which means the time it takes, it grows at the same rate as the string, not exponentially.
So we're not doing tons of extra checks like in the brute force method.
Exactly.
But how do we even keep track of which characters we've already seen in that window?
Right.
I'm guessing there's got to be some way to instantly check for those duplicates.
There is, and this is where we get a little help from a really useful data structure.
Okay.
It's called a hash set.
Okay.
So think of it like a bag that only allows one of each item, right? Only unique items. And you can instantly check, is this thing already in the bag? So as we slide our window across, right, we add each new character to the hash set.
Okay.
If we hit one that's already there, boom. Duplicate.
Okay.
Gotta adjust that window.
So if we hit a duplicate, what do? Do we start a whole new window from there?
Not quite. We want the longest substring. So instead of starting over, we just shrink the window, but from the left side until that duplicate is out of there.
Yep.
This way, the window always has only unique characters.
Okay. I think I'm starting to get this sliding window thing.
Yeah.
So we slide along, expanding for new characters, shrinking when we see duplicates. But how do we know, what the length of the longest substring is?
As we do all this sliding, we're keeping track of the maximum length our window hits.
Okay.
By the end, that max length, that's the length of our longest substring, the one with no repeating characters.
This is so clever.
Yeah?
It's amazing we went from, a really slow process to something so much faster.
I know, right?
I'm guessing that's, the power of choosing the right way to store the data and the right approach.
Exactly.
Yeah.
But understanding these like fundamental concepts, we can totally change how our code performs, especially with massive data.
Yeah.
Now, I'm wondering, could we make this even more efficient, this sliding window? What do you think?
I feel like there's got to be like, some way to make this even faster, even more efficient.
You're right. There is.
Okay, awesome.
While that hash set, it's a solid approach, there's a way we can do even better.
Okay.
But we need to know a little something specific about the characters we're dealing with.
Okay.
So let's say for this, we're only using lowercase English letters.
Okay, lowercase English letters. So that means we've got, what, like 26 characters?
Exactly, only 26. Could we use that somehow, you think?
I'm thinking maybe we could use that to, like, I don't know, keep track of what we've seen already.
You're on the right track.
Okay.
So instead of a hash set, what if we just use a simple array?
Okay.
We know we only have 26 possible characters, right?
Yeah.
So our array, it only needs 26 slots.
Okay.
Yeah.
So instead of all that hashing, like calculating the hash and checking the hash set, we could just use the character itself as like the index in our array.
Exactly.
Yeah.
We can use the ASCII value of the character to go directly to that slot in the array. It's like designated parking, but for each letter. No more searching, no collisions.
Okay. Walk me through this. Let's say we have the letter C.
Okay.
How would we mark that as like seen in the array?
Well, ASCII value of C, that's 99.
Oh.
ASCII for A is 97.
Right.
So C minus A gives us 2. We'd use index 2 in the array for C.
Okay.
We could put a 1 there, means we've seen it. 0 means we haven't.
So we're like trading a little bit of space, right? A 26 element array for a big speed boost because we're cutting out all those hashing calculations.
Exactly. And this works best if we have a limited character set and we know what it is.
Okay.
If we were dealing with like the whole Unicode set, our array would be gigantic.
Yeah, that makes sense.
And the space it takes up, it might not be worth the speed boost.
So it's about picking the right tool for the job.
Right.
Okay.
Yeah.
But I'm curious, like, how much faster does it actually make things? Like, in cases where we can use this array trick.
Well, the big O notation, that stays O of n for the time it takes. But the constant factor, that gets much smaller.
Okay.
And in the real world, where every millisecond counts, this tiny change, it can be huge. And it's a great example of how knowing the little things about algorithms and data structures, it can really improve performance.
It's like, it's not just about finding a totally different approach. It's about tuning the little things.
Right.
But with all this talk about optimization and stuff, I realized we haven't even talked about, like, where is this used in the real world?
Oh, totally.
Can you give us some examples?
You actually already mentioned one, right? Finding those unique gene sequences in DNA.
Oh, yeah.
So if you have to analyze a huge DNA strand, this algorithm, it becomes essential for efficiently finding those, really important sequences.
So, like, applications that are literally pushing science forward.
Yeah, pretty cool, huh?
Yeah. Is there anywhere else this algorithm shines?
Yeah. Another common one is plagiarism detection.
Okay.
Comparing two big documents
to
see if there's any chunks that match.
Okay, yeah, I see that.
Yeah.
Like, we could use it to find the longest matching substring.
Exactly.
I'm guessing it's not just like blindly run the algorithm, though.
Well, you got to think about things like, what if someone paraphrases?
Right.
Or uses synonyms?
Yeah.
Got to consider the overall context.
Right.
But being able to find matching substrings really fast, that's a super valuable tool for that kind of stuff.
I'm starting to see how powerful this, seemingly simple algorithm is.
Yeah.
From like DNA analysis to catching plagiarists.
I know, right?
It's doing important work behind the scenes.
It really shows that even basic algorithms can have a big impact on the real world. It's all about understanding the problem, picking the right tools, and always trying to be efficient.
So we've covered the problem, the brute force approach, and really gotten into that sliding window technique with some neat optimizations.
We have.
But I know there's some tricky parts to actually, making this algorithm work in code.
Uh-huh.
What are some things people should watch out for?
That's a good question. One thing that trips people up is they forget about those edge cases.
Edge cases?
Yeah, like what if the string is empty?
Oh.
Or it's only got one character?
Right.
You always got to make sure your code can handle those weird scenarios.
Without, like, crashing or giving a wrong answer.
Exactly.
So how do we handle those in the code? Do we need, like, a ton of if statements?
It's usually not that bad.
Okay.
Just a few checks at the start of your function.
Yeah.
Like if the string's length is 0 or 1, just return the right answer immediately.
Yeah.
It's like a safety net before you start the main routine.
Gotcha. So catch those unusual cases early on. Anything else people commonly mess up with this algorithm?
Another one is people don't quite get that left pointer in the sliding window.
Yeah.
Like its role.
Yeah, because it kind of jumps around, especially when you hit a duplicate.
Exactly. You got to remember it marks the start of the valid substring that we're looking at right now. So if you find a duplicate, you got to move that left pointer to make sure that duplicate's not in the window anymore.
And we move it to one position after we last saw that duplicate, right?
Yes. Very important detail.
Okay.
It's all about keeping that sliding window, pure.
Right,
you always want it to be a substring with only unique characters.
So debugging this, it's almost like you got to picture that window in your head and watch how those pointers move.
Visualizing it can really help.
Yeah.
Especially if you're hunting a bug. Just draw it out. Imagine that window sliding. Makes the logic way clearer.
Okay. So we've got edge cases, the left pointer. Anything else to be careful about?
One last thing, picking the right data structure.
Okay.
We talked about how a hash set, it's a good general solution to track unique characters. But if you know you have a specific character set, that array optimization, that can be a game changer.
Yeah, that's the one where we use the character itself as the index.
Exactly. But you got to pick the right tool for the job, right?
Right.
If you just use an array without thinking about the character set, you might end up with a huge array that wastes a ton of memory.
So it's know your problem and choose wisely.
Exactly. Understand the trade-offs, make smart choices based on what you're dealing with.
It's all about context.
It is.
So it really is all about context. But this has been such a cool deep dive into this, the longest substring problem.
It has.
We went from brute force, which felt like, swimming through mud, to this sliding window, which is, so elegant and fast.
Pretty neat, huh?
It is. And who knew this, kind of simple problem had so many uses? Genomics, plagiarism.
It's everywhere.
It really shows. The fundamentals are important, and there's always something new to learn, even with these classic problems.
I totally agree.
Thanks for joining us on AI.Code.Cast.
Yeah, thanks, everyone.
We hope you enjoyed this deep dive, and hey, we encourage you, try this algorithm out, see where you can use it.
Yeah, have some fun with it.
Until next time, happy coding.